Hey, I have realized, I have brought to my own attention that I made a mistake in number 10. I did everything right except for when I made the force diagram. I'm not going to talk through the details of the problem. I'm assuming that you're up to speed on what this problem is about. And you probably caught the mistake, maybe. What I did, this is a 20-degree angle here, and for whatever reason, my brain processed it. I thought it was 30 degrees when I was doing these things. I think I did this one right. This is 0.47 mg. That's 0.5 mg times the cosine of 20. But then for some reason I did sine of 20, and I was like, oh, that's 1/2. Like sine of 30 is 1/2, of course. And so I got the wrong thing here, and that considerably changes the problem, and it makes it really, I think, more really want to do A and B now. So I'm going to do that here real quick. So let's get the right number there. So 0.5 times the sine of 20 is 0.17 mg. And that means the normal force here, since this is 0.17, I've got that going up already. The normal force is whatever it needs to be to balance out forces along this direction. So that's going to have to be 0.83 mg, because a 0.83 mg and a 0.17 mg will add up together to balance this. Okay, so now the first thing we have to check is there enough static friction available? Is the maximum amount of static friction going to be enough to handle that? So let's see. How much static friction is there? In part A, I think the coefficients were 0.6 and some other number that's not going to end up mattering because we're not going to use it. But we don't know that yet. So 0.6 times the normal force, and that's 0.83 mg. So 0.6 times 0.83, that's right about 0.50 mg. And is that enough? That's the maximum amount of static friction that there could be. Is it equal to or bigger than this? Yes, it is. So that means the force of static friction. It's not this. That's the maximum that it could be. Of course, if it was this, then this thing would be like very weirdly accelerating backwards, and that's just not going to happen. It's as much as it needs to be to balance this. So how much static friction is there? This much. Could there be more? Yeah, it could go up a little bit more. And then once you pass that, it would break. So here, what does this mean? In part A, these are balanced, so that means the acceleration is 0. But what about in part B? What if we drop the static coefficient to 0.4? And this is the one, this is now going to play out like what I did in the wrong version of 10A from the notes video. So the static coefficient, now we still need to check that. What is the maximum amount of static friction available? None of this has changed, so now I have 0.4 times the normal force, and I mean our intuition would probably be, yeah, that was really close, so this is surely not going to be enough. So 0.4 times that 0.83 is going to be 0.33 mg. That is the maximum amount of static friction that there could be. Is that enough to balance this? No. We could say not enough. So that means that's not happening. It means that we have to go to the kinetic model. So that's the kinetic coefficient times the normal force. So how much is there going to be? There's going to be, what's that going to be, 0.25, I suppose. 0.3 times 23 is about 0.25 mg. And then now I can write my sum of all forces is equal to mass times acceleration. So here I've got 0.47 mg, and now I know how much kinetic friction I have, 0.25 mg. That's going to be equal to mass times acceleration. So it looks like the acceleration is going to be 0.22 g. All the m's cancel. And if you want to put a number on that, you can. It's about 2.2 meters per second squared. That's that problem done with the correct answers. So apologies for what happened in the notes. Everything that I did in the notes was fine, except that this number was wrong, and of course that changed that, and that was the real issue there. But this setup was all good, so you can go back and fix that. All right, thanks.